Have you ever just stopped and wondered how your phone can look at a photo and instantly know there's a dog in it? I mean, it feels like magic, right? Well, today, we're going to pull back the curtain on that magic trick. We're going to start with the simplest line of code and build our way up brick by brick until we understand the very heart of artificial intelligence. So, let's get into it. So this is the big question we're tackling. How do you teach a box of wires and silicon, a computer, to do something that feels so, well, human? It's not magic, I promise. It's actually a really fascinating process of building with digital Legos. And by the time we're done here, you are going to get exactly how it's done. All right, here's our game plan. First up, we need a foundation, which is the language we'll use. Then we'll grab our first bricks, some really basic tools. After that, we'll see how to assemble those bricks. Then comes the cool part, the blueprint for an AI brain. And finally, we'll see how we actually bring that whole thing to life. Okay, section 1, the foundation. Before we can build anything, we have to be able to talk to our construction crew. In this case, the computer. And that means we need a language that both we and the computer can understand. You know, it's kind of like toothpaste. You've got Colgate, you've got Crest. They all clean your teeth, right? But they have slightly different flavors, different features, and maybe you prefer one over the other. Programming languages are exactly the same. They all let you give instructions to a computer, they just have different styles and strengths. For our project, our language of choice is going to be Python. And there's a really simple reason for that. It's famous for being easy to read. A lot of Python code almost looks like plain English, which makes it absolutely perfect for beginners who are just starting out, but also powerful enough to build some of the most complex AI systems on the planet. All right, moving on to section 2, the first bricks. We've picked our language, now it's time to actually pick up our tools. Because before you can build a giant skyscraper, you have to understand the single most important part, the brick. And in programming, that means we need to know how to handle information. So, our most basic fundamental brick is something called a variable. And honestly, the best way to think about it is just a labeled box. That's it. You put a piece of information inside, say a number, and you slap a label on the box so you can find it again later. Simple as that. Oh, and a little tip. In Python, it's common to name these boxes with lowercase letters and underscores, just to keep everything looking clean. Now here's something that's really important. The computer needs to know what kind of stuff you're putting in the box. Is it a word, or is it a number you can do math with? This idea is called a data type. For now, we only need to worry about the two most basic ones, text and numbers. And little side note, for some old school reasons, programmers almost always call text strings. And this is where that difference really matters. With numbers, it's obvious, right? 1 + 1 = 2. The computer gets that. But what about with text? What would the letter A plus the letter A even mean? To the computer, they're just symbols, not quantities. You can't do math on them, and that's the key distinction. So when we say do math, this is pretty much what we're talking about. These basic operators, your plus, minus, multiply, and divide signs, they're the real workhorses. They're what let us take those number-filled boxes and actually do useful things with them. Okay, on to section 3. We have our bricks, our variables. But you know, a giant pile of bricks on the ground isn't a house. So now, we need to figure out how to start putting them together into something a bit more organized. The simplest way to start organizing our data bricks is with something called a list, and it is exactly what it sounds like. Think of a shopping list. It's just a bunch of items, one after another in a specific order. So for example, we could make one list called scores and just pop 3 different numbers into it. It's a super simple idea, but unbelievably powerful. So, what if you have a set of steps that you need to do over and over and over again? Well, you don't want to write them out every single time. Instead, you bundle them up into a function. The recipe analogy here is perfect. You write the recipe once, give it a name, and then anytime you need it, you just call its name, give it some ingredients, we call those inputs, and bam, it gives you back the finished dish, the output. Okay, let's just hit pause for a second. We've talked about labeled boxes, shopping lists, and recipes. These are really simple ideas. So how in the world do we get from that to a computer that can recognize a dog? How do we build something that feels intelligent out of such basic parts? Well, the secret is in the blueprint. And here we are, section 4, the blueprint. This is where it gets really cool, because we use these simple programming bricks to build a very specific kind of structure, an architecture that's actually inspired by the most powerful computer we know of, the human brain. We call this special blueprint a neural network.
And I want you to just imagine a huge, complicated web of interconnected dots, which we call neurons. These dots are all organized into layers, and the whole structure is designed to find patterns and information in a way that's, well, a lot like how our own brains work. So let's break that down. Even a super simple network has three main parts. First, you've got the input layer. That's the front door. For our dog problem, this is where every single pixel of that dog photo enters the system. Then, you've got the hidden layers. This is where all the magic happens, the thinking. The neurons in here fire and pass messages to each other, trying to spot patterns like pointy ears or fur or a wet nose. And finally, you have the output layer, which takes all that work and makes a final decision. It boils everything down to one simple answer. Yep, that's a dog, or nope, not a dog.
And that brings us to our final section, bringing it to life. We have our language, we have our bricks, we've even built the blueprint for our AI brain. But right now, it's an empty building. It's just a structure. It doesn't actually do anything yet. To make it come alive, we have to teach it. We have to train it.
This whole process is called training. And honestly, it's a lot like teaching a toddler. You show the network a picture and say, this is a dog. Then you show it another picture and say, this is a cat. It is not a dog. And you do this thousands or even millions of times. And with every single picture, the network makes a guess and we tell it whether it got it right or wrong.
So how exactly do we correct a computer? It's not like we could just say, no, that's wrong. We need to tell it how wrong it was. And that's the job of something called a loss function. It's basically just a piece of math that calculates a wrongness score. A perfect guess gets a score of 0. A really terrible guess, it's a really high score. And just like that, the entire goal of training becomes a game. Get that score as close to 0 as you possibly can.
And this right here, this is the engine of all machine learning. It's a simple loop. First, the network predicts. It looks at a picture and says, I think that's a dog. Then we calculate the loss. We tell it, you were about 30% wrong on that one. Then, based on that score, it will adjust all of its internal connections, just a tiny, tiny bit, to try and do better next time. And then it repeats, on to the next picture, and the next, and the next, millions of times.
Now, this whole adjustment process has a kind of scary sounding name, gradient descent. But don't worry about the name. All it really means is go down the steepest part of the slope. The best analogy is to imagine a ball sitting on a hilly landscape. The very top of the hills is where the error score is super high. The bottom of the valleys is where the error is super low. All gradient descent does is look at where the ball is, find the steepest way down, and nudge the ball in that direction. It just keeps nudging it downhill until it eventually settles at the bottom of a valley, the point of lowest possible error.
So let's just tie this all together one last time. We used our really simple bricks, things like variables and functions, to build a blueprint for an AI brain, a neural network. Then, that learning loop we talked about, it acted like our construction crew, running millions and millions of times, making tiny adjustments to that blueprint until it turned into a finished building that could actually do something incredible, like recognize a picture of a dog.
And there you have it. From simple code bricks to a truly intelligent building, we've just walked through the fundamental recipe behind almost all modern machine learning. This exact same idea, predict, measure your error, adjust, and repeat, that's what powers the most advanced AI systems in the world today. So now that you know the basic recipe, the only question left is, what problems are we going to solve with it next?